So we'll be tackling the basic forms of energy before we going to touch the work and heat. So as a review, we will have these basic forms. Number one is the gravitational, or this called potential energy. This means that the energy that an object possesses at a height or elevation given z above some zero reference level. So that is given by this potential energy Pe is equivalent to mass times gravity times c, where z is an elevation or height, and the unit is in joules. So per kilogram, this is the small Pe is equivalent to Gz, and this is joule per kilogram. And the G is the gravitational acceleration, which is in meter per second squared. So this is a review, since you already tackled this one in our physics. Okay, so that at a given elevation, the highest potential energy is in the top. So given this one, this is your ground and this is your top. So at given height or elevation, the given z here, so at the given elevation, so your potential energy would be greater than the potential energy, example at point 1 here and point 2. So the potential energy at point 1 is greater than the potential energy at point 2, right? Okay, so this is in mass times gravity times the elevation. So for example, if you have this man here at the top, so given the mass, there is an elevation also given, and also the gravitational acceleration, which is g, is given as 9.81 meter per second squared. So in SI units, we have the joule per kilogram, or just simply joules, given the height times gravity times this elevation. Okay, that's for the number one basic forms of energy. So we have here also the number 2, we have the kinetic energy. So what is this kinetic energy? So this is energy by virtue of velocity. So this is equivalent to Ke is equivalent to 1/2 times mass times the square of the velocity. Also the unit is in joules, or this is v squared over 2. When this is in the unit is joule per kilogram. So wherein the v is the average velocity, it is in meter per second. Okay, so to give you an elevation, so we have here, example, this is a ball. We have a ball here to given height. So the kinetic energy here, example at point 1, equal to 0. So given this elevation, so at the ground level, we have that your kinetic energy, this is 0.1 and 0.2. So the kinetic energy at 0.2 is greater than the kinetic energy at 0.1. So when your body is at rest, meaning to say you have no potential energy, or you have zero kinetic energy. So if your body keeps on moving, so it increases its kinetic energy. Okay, so we proceed to the third basic forms of energy, which is the internal energy. So by definition, this is the sum of the energies of all molecules in a system. Energies that appear in several complex forms, mostly kinetic. So we're dealing here with the internal energy, deals with the molecules in a system. Okay, so that is the unit is in joules for the capital U, the total energy, or the total internal energy, and small letter u, this is in U per kilogram. It is in joule per kilogram. Okay, so we have here this kind of the work and heat. So the work and heat is also we call this an energy. Okay, so by definition, the product of this of the displacement of the body and the component of the force in the direction of the displacement. For example, here we have this one, we have the box. So if you apply force here, and we have this distance here, d, so we know that this is the product. Work is the product of this one, force times this displacement. So this is also a review, since these are tackled in your physics. So if the displacement is 0, meaning to say you have no work, or your work is 0. Okay, no matter how big your force is. And work is energy in transition, that is, it exists only when a force is moving through a distance. Okay, so this is, so if the direction is to this point here, for example, this is your point 1 and this is your point 2. So you have this displacement. You have this displacement is equivalent to d2 minus d1. This is d2 minus d1. Okay. That is your d2 minus d1. So that is your displacement. Okay. So since work is energy in transition, it only exists when a force is moving through a distance. So given a system here, given the surroundings and its boundary, we tackle this one in our basic concepts as in the introduction of thermodynamics. So we have the sign convention for work. Okay, so given the surroundings and the system and boundary. So if your work here is going to the system, meaning this is your negative work. And if a system produces work, or you have an output of work, you have this positive sign. Okay? You have the positive sign of your work. So, here. Okay. So, by that, we can have this network, which is W net, which is equivalent to the summation of work in minus the summation of work out. Okay, so if you have so many, for example, you have that one, it's negative work, for example, work 1, work 2. So, example, you have also this work 2, and so on and so forth. You have so many work acting on your system. So we have this the network. So this is simply the summation of your work in minus the summation of work out. Okay. So we have this one. You have the forms of network. One is the boundary work, or this WB. This, of course, because the mass of a system causes a force to act on the boundary, either to expand it, or this is a closed system, or to cross it, or this is called the open system. Second is the shaft work, or the WS. This is work crossing the boundary in the form of a rotating shaft or electrical work. Okay, let's discuss further this. What is this boundary work and this shaft work? We have this boundary work. We have number one, this we will consider the closed system, or this is called the non-flow work. So considering a constant pressure or an isobaric process, constant pressure, we have for the non-flow work, the work 1 and 2 is equivalent to force times the D. Okay, or this is force times the displacement, or this the work from 1 to 2 is equivalent to since force is, or since pressure is force over A, or area, so we have the force is pressure times A. Okay, so that's why we have this pressure times A times this delta L, or that displacement. So we know that work from 1 to 2 is equivalent to pressure times, we know that the volume is area times the length. Okay, so that's why we have this delta V here. Okay, you have that delta V. So we know that work is a form of energy, and you have this displacement. You have the at the same direction of your force. So notice here we have work 1 to 2. So given a state here, we have your point 1, and this is your point 2 here. You cannot say that you have your work at point 1 and you have your work at point 2. Why? Because work is a path function. You can only say that you have work at point 1 if it is a property, right? So take note therefore that work is not a property, and work is a path function. So you have a path here from point 1 to point 2, or at state 1 or at state 2. So that's why we always define here as, or we always write that is work 1 to 2. Not work at point 1, not work at point 2, but it is work from point 1 to 2, because our work is a path function. Okay? It is a path function. So we have in differential form, this is the inexact differential W is equivalent to P dV, wherein your W and F and the integral of P dV, this is your non-flow work. N is the inexact differential, that is a process dependent, and the PDV represents the area under the curve in the PV plane. So if we have the area under the curve, if you have this PV here, and this is pressure volume. For example, here you have this point 1. You have this point 1 here. This is your PV. PV. So you have at point 1 here, and you have your point 2. Okay, so that is an exact differential. So here this is an exact differential. So this one, you have a path, that one, or you have the path also here, and you have also this path here. And this is an exact differential. So you have your path A, for example. You have this path B here. Okay. So the area under the curve here, this is your area under the curve. This is the area under your curve. that is P dV. So therefore we can write this one as the integral of we have the limit from 1 to 2. This is shear work in exact differential. This is because it is path dependent. So we have this one, work from 1 to 2. So work here is a path function. It's a path function because this is not the property. This is path function, this is path dependent. Okay. So we proceed here for the boundary work. That is for the closed system for this the number 1. So what if for the open system? The open system is called the flow work. Okay, the flow work is WF is to flow work, and this is pressure times A times L, or also we can write that as P L squared times L, and P L to the cube, and we know that L cube is also a volume, so we have WF is P times V. Okay. So next is the shaft work. WS in thermodynamic definition of work. The work is done by a system on its surroundings if the sole effect on everything external to the system could have been the raising of a weight. Okay, it could have been the raising of a weight. Okay. So we have this in exact differential work here. This integral of 1 to 2, and that is that one, right? 1 to 2, this is a path function. So we define what is path in our previous discussion. So from state 1 to state 2, work from 1 to 2 is done by a force moving through a distance. So this work 1 and 2 here is equivalent to this integral of f dx from 1 to 2. Okay. Or we have here this one. This is f dx. So if we have one-dimensional system, we have work 1 and 2 for one-dimensional system. This is 1 to 2 f dx. or simply we have this one. We go back to this one. F times dx. Okay. So from these equations, we notice that the work differential is inexact. This is an important point, as work integrals will be path dependent, and work will not be a state variable for a system. Here, the force F is a three-dimensional force vector. X is a three-dimensional distance vector, and is the dot product operator. Recall that the dot product of two vectors yields a scalar. The terms F and X are scalar equivalents valid for one-dimensional systems. So the units of force are in Newton. Those of distance are m. So the units of work are Newton meter, which have been defined as joules. Okay. You have the unit work, the Newton meter, or this is equivalent to your joule. Okay. So again, if we have a given system and we have work here, we have this work here. So the sign convention is this one. We have this is our system here. So we have the summation of work, and here the summation of work also. Okay, so this is negative. Example, this is here, work in and work out. So this is positive and this is negative. Okay. Okay, we have an example here. You have this example. You have find the work. This find the work. Find the work for the constant volume process. Constant volume process, or this is also correct. So it says dV is equal to 0. So from our equation, we have here this one, work from 1 to 2. This is the integral of 1 to 2 p dV. So since this is in constant volume process, so we have this dV here is equal to 0. So there is no work for a constant volume process, as you can see in this equation. You have no work, or your work is 0. And the same is true to polytropic process. For polytropic process, polytropic process with the n approaches to infinity, our work is also 0. Okay. Okay, example number 2. We have this example number 2. You have an ideal gas. Ideal gas undergoes a process. At the initial state, it is isothermally compressed to state 2. So there is a compression. Isothermally, meaning constant temperature. Isothermally compressed to state 2. Then it is isobarically compressed to final state 3. Then at state 3, we have this isobaric process or constant pressure. Isobaric process. So find the work. Find the work. Okay, we will draw the PV diagram here in order to analyze our problem. Okay, so we have this P, V, we have the isothermal. So for example, this is our point 1 and this is our point 2. So that is an isothermal process. T is constant here, where temperature is constant, and isobaric meaning constant pressure from point 2 to point 3. So you have here that one, you have that one. Okay, so this is our PV diagram. Okay, So solution. So we have work. We have to determine from work 1 to 3. So we have work 1 to 2 plus work 2 to 3. Okay, so by definition or by our formula, we have PDV work from 1 to 2 plus the integral of 2 to 3 PDV. Okay, so remember that we have this gas. This is an ideal gas. We have the PV is equivalent to MRT here. Okay, so since we have the isothermal process for our from process 1 to 2, we have that isothermal process. Okay, so this temperature is constant. We have mass is constant. We have this R is constant. Okay, so here we have this equivalent of our P. So this is MRT over V. Okay, so we have MRT over V, then dV, integral of 1 to 2 plus 1 to 2 P. No, this is 2 to 3. To 3 PTV. Okay, so since here this is constant because we have T is constant, we have isothermal. Okay, so we have here MRT, this is dV, integral of 1 to 2 dV over V, plus, so we have this isobaric from the process 2 to 3, or at state 2 to 3, so isobaric, so we have this constant pressure, so that is integral of 2 to 3 dV. Okay, so therefore we have this one. You have the MRT 1 ln of V2 over V1 plus this pressure here, this is V3 minus V2. Or we have this one, P1 V1 this is P1 B1 because MRT is equivalent to PV, so you have P1 V1 ln of V2 over V1 plus P V3 minus V2. That is your work your total work. Okay. So the work done is less than 0 since we know the volume V2 is less than the volume V1. And the volume V3 is less than V2. Hence we have a work of compression. Means a negative sign convention and implies work required or work is done on the system. So our work is negative, so it requires work. Okay, work is done on the system. Okay, so how do we know that the V2 is less than V1 and the volume V3 is less than V2? So by our diagram here, we can recall. This is your PV diagram. So you can say that V2 is lesser than V1 and your V3 is lesser than V2. So by that, so V2 is lesser than V1. Okay, and V3 is lesser than V2, so we have a negative work here. Okay. Okay. So the meaning of the negative work, meaning we have a required work for our system.